Weber. So F is a totally real field. It is a finite abelian CM extension of F. G is the Galois group, and so we reduce proving the strong version of Brumer-Stark conjecture, this conjecture of Burns, Kurihara, and Sano, to constructing some cohomology class. And as I told you, our way to do it is using Ribet's method of constructing global cohomology classes with prescribed local behavior. And I introduced some Eisenstein series. So let me remind you of this weird Eisenstein series that I wrote down last time. So recall that we had this WK psi 1. This is summation m dividing t. So t, recall, was product of all primes in this set T that we had. Mu m, the Mobius function, psi applied to m. M to the k, and then this group being valued Eisenstein series as usual, level raised to m. That was the Eisenstein series. So now I'll tell you what the constant terms of these things are. This one just compute, well, at infinity at least. And so the constant terms are as follows. Constant term at infinity, the normalized constant terms are 2 to the minus n times some factor, so some Gauss sum and so on. I written it down here. Theta s infinity t. So remember our simplifying assumption that this is unramified. That's our simplifying assumption. And so s is just s infinity, and t is whatever t we require to take. 1 minus k. So this is if k is bigger than 1, and it's equal to 2 to the minus n, theta s infinity t 0 plus, so again some Gauss sum. So this is Gauss sum. I think that's the only thing. So you need some Galois Gauss sum, I guess. That's why I did not write it down here. But I'll not say what this exactly is. But there's some explicit factor there, t, but with this involution applied to it. Yeah, so that's the, so if k is 1. And of course, if you are not in the situation where h over f is unramified, you have to take other cases as well, depending on what the conductor of h over f is. But yeah, so it's good that we are in this simplifying situation. I don't have to write. All right. So what you do is now you put f sub k, this group ring valued thing, which is so you take a particular linear combination, and I'll tell you what the objects in this are in a minute, but let me write it down first. So you take the weight 1 thing of this, but it's weight 1, and I want the weights to be equal, so I'll multiply it by some auxiliary thing. This is lift of Hasse invariant. And then I scale it with theta s infinity t 0 over theta s infinity t 1 minus k wk psi 1. So that's the weight 1 thing, but I normalize the, I put the coefficient in this way. Then minus theta. Okay, that's not quite what I want, I think. So let me put tilde here, and then I'll change this. So theta s infinity t 0, but with this thing, and then I have to And then another auxiliary thing. So I'll tell you what these two objects are. But right now, let me. So, fine. So I'll tell you now what the V and the K are. So VK is this VK minus 1. This is lift of Hasse invariant. So this was constructed, but this is in a, well, the first time I saw it was in a paper of Wiles, and he attributes it to eta. This is lift of Hasse invariant. So this is in M K minus 1 with yeah. So level is 1, character is 1, and then VK is congruent to 1 modulo some large power of P. So this M depends on what. So, and here K minus 1 is congruent to 0 modulo. So yeah, all these quantities are kind of dependent on what the capital N is. But this is lift of Hasse or some power of it to get the appropriate congruence. Okay, so that's one of the objects, and then the other object is some group ring thing that kind of maybe appears in some cases in this appendix of Chai to Wiles's paper on main conjecture, but in the form that we want, this is due to Jesse Silliman. So for all K large enough, he proves that the appropriate constant term map from the space of modular forms is surjective onto, yeah. So you need some compatibility between the constant terms at different cusps. It has to be a K equivariant. So, but so long as that is satisfied, the map, you just take the tuple which are sort of a K equivariant, and then the map is surjective. So so there exists GK psi in MK. Let me write it like this. With normalized constant terms given by, yeah, so I'm going to write something that I won't define, but normalized constant terms. So these are constant terms at all cusps now. I'm sort of worried about all cusps. So it's sine of norm of A. So these quantities, this ideal A and another ideal B that I write down will depend on the cusp at cusp A. So I'm not going to sort of tell you what this notation means for the cusp, and I'm not going to tell you how these things are defined using the cusp. But anyway, so you have this, you want sort of constant terms to be like this at various cusps. In particular, at infinity, you just want 1. And this theorem of Jesse tells you that there exists a group ring family like this with those constant terms. Okay. So that's all fine. Now, the other point, yeah, somehow is, yeah, I'm putting something in the group ring in denominators, so maybe that should alarm you a little bit. And there's this tilde, so let me.
I still don't quite understand what makes this a group ring.
Which one?
Well, you're referring to these GKs, no? Or what do you?
Yeah, GK, that's just, I mean, I'm not telling you what the family is. I'm just saying, well, group ring, because you see this is the group ring valued. This is from GF to the G cross. So it's not a character taking values in a field.
Oh.
So when you specialize with various characters of G, you get the usual modular form with that particular event. That's what I mean by grouping.
And piggybacking off of that, this VK is not grouping value, right?
VK is not group ring valued, so that kind of messes things up a little bit. Yeah. But yes. Okay. So what do I want to say? Oh yeah, I want to tell you about this ratio. This is kind of some unusual thing. So let me write down something, but the screen goes away. Okay, all right. So here's a lemma. So for A congruent to 1 modulo P minus 1 into P to the N, for N sufficiently, I mean, okay, for K also sufficiently large and N also sufficiently large, you define this X to be theta S infinity T, 1 minus K over theta S infinity T 0. So that's the reciprocal of the thing appearing here. And anyway, I'm going to multiply this whole thing by that X. So I'm going to take, yeah, this will go away. You'll have an X here and an X here. So maybe that's how I should have written it. That's why that F tilde there. So a priori, this is an element in the, so this is non-zero, right? We are sticking to the minus side. So all the values here are non-zero. So this is a well-defined element in the total ring of fractions of uh, ZG minus. And yeah, so for n and k sufficiently large, what happens is that this is actually belongs to the to ZG minus itself rather than the total ring of fractions. So what I'm saying is that this will be very close to this periodically. So when you take the ratio, you yeah, maybe yeah. Right. So okay, so now we fix an odd prime p. But yeah, I think at this point I don't really need it to be odd as long as I take 4 here. But anyway. Okay, so how does one show this? So the idea for this is you just look at p-adical functions, right? So you look at S. So SP is S infinity union all times V that divide P. So I just look at this. This thing is whatever my theta S infinity T is times the Euler factors at P. So this is 1 minus Frobenius at P, norm of P to the K minus 1. I have to remove Euler factors at P, and this is what one does. And so you, so the the fact that p-adical functions exist, so this is the mean rivet and Casablancas. It says that this theta is pt 1 minus k minus theta that's infinity. Well, okay, let me write it. It's sp0 0. This is congruent to 0 modulo some large power of p. Okay, so n will always be large enough. I don't want to use different variables for all those things. And now if I divide this by my S infinity, theta S infinity t, then I get, what do I get? I get theta S infinity t 1 minus k over theta S infinity t 0 product V dividing P 1 minus sigma inverse norm of P to the K minus 1 minus. Sorry.
Sigma V.
Oh, yeah.
Yeah.
Easy. Okay.
Yeah.
Thanks. Anyway, and then product overall P dividing P 1 minus sigma P inverse. Right. And this is a, this is a group ring element. And this thing is a unit for k bigger than 1. And so this thing is in the group ring, right? For large enough n. So that's how this lemma is proved. Yeah, so furthermore, because this is a unit, this x is congruent to, I mean, this is not just, this x is congruent to this element modulo the maximal ideal. And you see this, so if P splits in, if primes above, I mean, by P, I mean this Gothic P, if Gothic P splits in H, so if Gothic P from here to here splits, then sigma P is 1, and you get a 0. So that's the case of trivial zeros, right? So the number of Gothic P's that split is equal to the order of vanishing of the p-adic function. This was proved by Samit and Pierre and Michael Spies and Matt Greenberg, and then away from p equal to 2 by Wiles before that. So, so this x, it sort of captures information about trivial zeros. So that's the remark. So x keeps track of trivial zeros. So although we don't use Iwasawa theory in proving Brumer star conjecture, sort of trivial zeros still come into the picture. Yeah, of the p-adic function. So this is, p is dividing p such that sigma p is 1. So that's what it keeps track. Okay, so having done all that, let me just write down the theorem that I want. So now,
But Mahesh,
Yeah.
one more time. So when you invert this x, you are interested in the inverse of it.
no, I'm going to clear it out. Yeah,
You-
yeah, because I think that's not. Wrote that a bit hurriedly, and so fk psi. Sorry, I should have done this. This is you take the ordinary projection, and then you clear everything out. So you write x w1 psi 1 vk minus 1 minus wk psi 1 minus 2 to the minus n. So that's kind of inconsequential for us because we are away from p equal to 2. And then theta s infinity t 0 gk psi. Okay. Now, what I'm going to, so the way so the reason I wrote it like this, because it's easier to see that this is semi-cuspidal in the sense that its constant term at infinity is 0, because the constant term of this guy is this plus this, right? And so the constant term of this is 1 at infinity, and the constant term of this is this at infinity. So you cancel, and this is also sort of, you can think of this as constant term being 1. So, well, it's not exactly 0, but it's 0 modulo some high power of p. Okay. And so that's at infinity. It's easy to see that that's what happens at infinity. Because of this thing, it's may not be exactly 0, but it's 0 modulo some high power of p. What you can show is that, so we compute constant terms of these Eisenstein series at all cusps, at least all cusps that are unramified at P, that doesn't appear in our case here because sort of P is not in the level, but yeah, if P were in the level, we compute constant term of this at all cusps unramified at P, and we show that those are highly divisible by P. And when that happens, you can modify your GK a little bit to make it actually zero at all those unramified cusps. And when you apply the ordinary projector, you actually get a cusp form, ordinary cusp form. So the theorem is that this is in SK T N or so that's kind of in a very sketchy way of saying that you get how you construct a cusp form. So yeah, so just a word of warning here. This GK is slightly different from the eventual GK that one has. But that also comes from Jesse's theorem. So I didn't explain what exactly I'm doing here. I think it's okay to keep the same notation. Okay, so yeah, once again, so you compute constant terms at all cusps, ramified over P, and then you show that they are zero, and then when you apply eta as idempotent, you get that you actually get a cusp form. All right, so now that we have a cusp form, we can. So this is the second arrow in Summit's diagram for Ribet's method. Now we go to Galois representations, from cusp forms to Galois representations. By the way, this will not be an eigenform. It's unlikely that it will be an eigenform in any case, except maybe even things are trivial. Okay, so yeah, before going to our Galois representations, let's look at some Hecky algebras and okay, so T tilde is the Hecky algebra acting on these, yeah, I don't know which way I write. So this is generated by TLs for all L not dividing T and P, and then by UPs for all P is dividing P. I ignored UTs, which is what you asked me yesterday, but yeah, we don't need them. Right? And then T is the one, oh, and diamond operators. I think I'm denoting them by SM. And this is just generated by the TLs. And the diamond operators. I don't consider the UPs. But a remark here is that this T and T tilde, these are reduced. This is, well, maybe Samit will tell you that this is not very important in sort of the way we prove Ribet's lemma now, but in the proof away from 2, we use that this is reduced. So, okay, so I won't say much about this now.
Who proved this reducedness?
I mean, well, it comes from the fact that you can write any element in this as by taking new forms and level raising it at P. So, and I don't know who proved that. Is it?
Well, it's just a. So I'm going to talk about this a bit like at length in my next talk, but the total ring of fractions of this is basically the product of the Hecke algebras of each of the individual forms. And so you just want to show there's no nilpotence for each individual form, but these forms are eigenvalues for all of these operators. And so
Ordinary at U.
right, they're except for they're eigenforms, so the total ring of fractions is basically just a field. Okay, except for the UP operator, but because you're at P and you're looking at the UP operator, the P ordinary condition gives you the use of this. So the point is there's no bad Hecke operators there. If you have old forms and bad Hecke operators, then you get stuff that's not reduced. And I'll talk about this at length tomorrow.
Yeah, I don't know.
And the rest of the argument wouldn't work if you passed it a nil reduction or something. Is that what you meant?
Yes, you need the Hecke algebra, the full of it. So if it's not reduced, you need the non-reduced Hecke algebra, and then you have to deal with that, which is what I'll talk about.
Yeah, because these UPs are what C is the L invariant. So to speak, right? So if you are passing to reduce thing, then you don't know what you're doing to.
Yeah.
Okay, so so let me, yeah, so what is the action of these things on our F psi? So you see, this thing is, it's here, right? So we understand how Hecke operators act on this, at least modulo some high power of P. We understand how they operate on this. We don't know anything about this, but we don't care. So this is E X W1 psi 1 minus WK psi 1 modulo X times theta. Yeah, okay. From now on, I'm just going to write this. I'm not going to write. Yeah, so theta is just theta S infinity T 0. Okay. All right. So maybe just yeah. So this congruence comes from that expression. But maybe just to point out, usually you construct a cusp form which is congruent to some Eisenstein series modulo the theoretical function or the L value. This now we get X times something. So this is a a deeper congruence, and this is important. So that's how sort of trivial zeros show up in what we do, although we don't use Iwasawa theoretic versions of all these objects. Okay, and this is important to get classes that are unramified at P, which is what we wanted, right? We want we want classes that are unramified away from T, and P is not in T. So what is the action of Hecke operators on these? Yeah, so then it's kind of, this is just a calculation that one does, and this thing is the p-adic cyclotomic character evaluated at L. So just Fk. So this is for L not dividing E P. And then UP just acts by 1. So Fk psi of UP is just Fk psi for all P dividing P. Okay. So Right. So so now I want to get a homomorphism from the algebra to the particular components of Hecke algebra into some ring. For that, let me look. I mean, I have to tell you which components I'm taking. So so let E over QP be a large enough finite extension. Finite extension. So what do I mean by large enough? Well, so that it contains coefficients of all eigenforms of level dividing T. So you take all normalized new forms of level dividing T and the coefficient, I mean, there are finitely many of those, and its coefficients will lie in some finite extensions of QP, and you just take E to contain all those things, right? And then O is just OE, and K is just the residue field of E. So first so there exists phi bar from T tilde to K. Yeah, such that, so because of this congruence, there exists this thing which takes phi bar of TL, which is just 1 plus psi L. Again, for all L not dividing T and P, and phi bar of UP is 1 for all primes above, P above P, and phi bar of all the diamond operators is just, oh yeah, I didn't tell you what the diamond operator does, but it just multiplies everything by psi. So that just comes from that congruence. And so, yeah, so we're just picking out the maximal ideal that contains the, yeah, so for the forms that are congruent to our Eisenstein series. So let M be I think this one yes, let M be this phi bar restricted to T kernel of this. And yeah, and then I look at the M-adic completions. So the important thing that we want to prove about this is some congruence from some homomorphism EM to a nice ring over the group ring. So this is like the analog of what you see a map from Hecke algebra into Iwasawa algebra in the group of mean conjecture. So theorem. So there exists a ZG minus algebra W and a ZG minus algebra homomorphism phi, which is supposed to be a lift of that. That's why that's phi bar and this is phi T tilde M to W, such that various things are satisfied. So so the structure, I mean, W is a ZG minus algebra. So there's a map from ZG minus to W, and that induces a, yeah, that will induce a map. So yeah, that's part of the theorem. So that induces a map from ZG minus mod X theta into W, and we want this to be injective. So this just kind of tells you that you're not taking W to be something trivial, right? It's large enough. So you're doing something non-trivial. Phi restricted to Tm is contained in this image. So I'll just identify the image by, I'm away from p equal to 2, so it doesn't matter where I put the minus sign, but maybe to be consistent with what Samit will say at 2. Okay, so when you restrict it to the Secchi algebra without the UP operators, you get this, and this is kind of simple to see because see it's supposed to do this to the Secchi operators that generate P. This is cyclotomic to the K minus 1 L plus psi of L. So that's why the image lies in this. And then there's the third property, which is somehow the important one, which is, so what happens at P? So P is the operators at P are the most interesting ones. So you take product overall P dividing P, UP minus psi P, right? So this is some element in the in T tilde. So what does the third thing say? If Y is an element of ZG minus such that, so when you apply phi to U, you get an element in W. And when you, so you can multiply this element in this with a scalar which comes from here. And if you get this, if you get that this is 0 in W, then you can actually conclude that Y is in the ideal generator. So if you want to recall what we wanted to show, we want to show that some fitting ideal is contained in the ideal generated by theta. So what we'll end up showing is that every element in the fitting ideal is annihilates this phi of U. So that's how we'll show that fitting ideal is contained in the ideal generated by theta. So this is these operators at UP see the L values. So this is, I mean, this all these things they go back to Greenberg Stevens and then the work of Samit with Henri and Rob. That you see L invariance in the UP operator. This is just a way of saying all these things so that it makes sense for group rings, group ring values. It's a more convenient way of saying it where it applies this way. Okay. So all right. So now we are ready to talk about Galois representations. Okay, so maybe a word about how this theorem is true. So the first, I won't say much about the first two things. So first is maybe an interesting thing that I would have liked to say a word about, but maybe I won't now. Second is just some calculation, like what happens here, and from that this follows. For the third one, let me say the following. So when you yeah, so maybe just for the third one, let me say the following. When you apply U to this, you get X times W1 psi comma 1 sub P. So here you just consider 1 with modulus P. You know, one has conductor, the trivial character has conductor 1, but you consider it with modulus P. So you can define everything with this modification. Modulo X theta. So you get something like this. And the fact that phi, yeah, so the fact that phi of u times y is 0 is same as saying that y times, yeah, so you look at the, this is normalized. So you look at the first Fourier coefficient of this, and that's 1. And from this, you can deduce that this thing actually lives inside x theta bar. So you just look at the first Fourier coefficient. Yeah, using these two calculations, you get this. And now remember, x was a non-zero divisor. Maybe I did not say this when I stated that lemma about x, but x was this ratio of theta s infinity t 1 minus k by theta s infinity t of 0. And these are all non-zero values. So this is a non-zero divisor in the group ring, and so you can cancel that out, and this gives you that this is here. So that's very roughly how this proof goes. Yeah, it's the same with 1. You have to look at various Fourier coefficient to conclude that if something goes to 0 in W from the structure map from ZG minus to W, if something goes to 0, then you look at various Fourier coefficient, I think at 1 and at primes above P, and you conclude that x times theta. It's contained in x times theta. All right, so now Galois representation. So let K.
So
Yeah.
this text. So non-zero divisor means EPG minus.
Yeah.
Or K satisfying the parity.
Yeah, so K will all, I mean, K is congruent to 1 modulo P minus 1 times.
Yeah, so.
Yeah,
not-
that's
not for all.
No, not for all. No, yeah, maybe I should have said that. My K will always be sort of periodically close to 1. Yeah, large enough and periodic. Yes, thank you. Yeah. Okay, so again, as Samit mentioned, this is Hida, Wiles, Carreol, Taylor, and so on. I won't write those names down. So there exists rho from GF to GL2 of K such that various properties are satisfied. Rho is unramified outside P and P. The characteristic polynomial of Frobenius at L, for L outside T and P, this is x squared minus TL x plus psi L epsilon cyclotomic character evaluated at L, so the usual thing. And then of course it's ordinary at T, so rho restricted to GP is psi theta P inverse something 0 and then theta P. Right, so it has this format when you restrict it. And then this is an unramified character as usual. And when you apply it to the geometric uniformizer, you get, sorry, geometric, Frobenius, you get U. So that's the convention. Okay. So now we want to talk about this third arrow in Samit's circle of Ribet's lemma, which is Ribet's lemma. So from this Galois representation, we want to construct some cohomology class. And this is where the sketch that I'm going to give completely breaks down at P equal to 2. And something else needs to be done, which will be covered in Samit's and Julia's talks together. Okay. So let me, in the remaining sort of 15 minutes that I have, let me tell you how one proceeds from here when P is different from 2. in particular, I want to sort of highlight how this, I mean, I have already sort of said why this X is important because we get a deeper confidence. And this sort of property, you see already X playing a role here in the proof that I sketched. So that's why I sketched the proof of this. If you did not have that deeper congruence, you wouldn't be able to conclude that things which are annihilated by phi u actually land in theta. So you need something deeper like that here. But there's one more place where one can highlight how X comes into picture, and that's what I'll do. Yeah, so I think Samit wanted me to write down an abstract version of Ribet's lemma, but I don't think I'm that.
You never do what I want you to.
So yes, I'm not doing that. But anyway, so the point is sort of from this point onwards, the proof in p equal to 2 is really different, much more wrong. But in away from p equal to 2, it is like the method that goes back to whiles and major whiles and so on, except for this trivial zeros that come into picture. So that's kind of the new part in Brumer Stark away from p equal to 2 in the Ribet's lemma. Okay, so we know that this PL is modulo x theta, that's like epsilon to the k minus 1 plus psi of L. So modulo x theta, this, yeah, there are too many x's. Modulo this x times theta, this polynomial has a factorization as x minus the cyclotomic to the power k minus 1 into x minus psi of L. And so as usual, Shebataref will give you the same factorization for all elements in. And because cyclotomic is 1 modulo. Yeah, I think maybe I'm not just working modulo sort of x theta, but also modulo some high powers of p. And this I may forget to write down. I'll write it down here once, but I forget to write it. So this is some large power of p depending on what p. So that's why my cyclotomic to the k minus 1 disappears. I hope I don't forget, but I mean, whenever I'm talking about congruence modulo x theta, this it will also be modulo some large power of p, and then we let that power. We go periodically closer and closer to 1. P goes to 1. Okay. Okay, maybe I'll just sort of say roughly what I want. Yeah, I won't state it exactly as Hamid wanted me to, but I'll say. So Ribet's lemma, roughly in this form that we want, is the following. So there exists a finitely generated TM module B and kappa. So I'll say a co-cycle in here, but we just want a homology class. Such that all those local properties are satisfied. So kappa satisfies local properties from last time. And yeah, so three things. It satisfies all the local properties. Fitting ideal of B is large enough. So this is contained in theta. And the third thing is image of, yeah, something about image of kappa. Let me not make that very precise. So image of kappa plus some finitely many elements that, okay, I'll write them down here. AP by CP, and I'll tell you later what these are. This generates so you see these are the three things that we wanted last time. Some local properties, and this one where I was denoting this by XVs right, last time. But now I can tell you exactly what they are, so I'll denote this. So how does one proceed from here? So first of all, I mean, what you do usually when you are trying to prove, when you prove main conjecture is you fix complex conjugation, and then you fix a basis of your two-dimensional vector space so that complex conjugation is diagonalized. Here you have to be a little more careful. So you show that there exists tau in, so this tau is some element in GF such that, well, in its image in is complex conjugation. And tau does not stabilize these. So you see this, there's a one-dimensional space coming from the form of this locally, right? So generated by 1, 0. So this does not, tau does not stabilize. Yeah, I'll denote it. Yeah, these one-dimensional spaces, these local one-dimensional. These subspaces that come from the form. So yeah, this is kind of not well, I mean, the way I've written it, it makes no sense, but what I want is there's a distinguished one-dimensional thing in here, and none, tau stabilizes none of those. So locally you want sort of the behavior to be different as possible from that particular form, right? So anyway, so there's some Chebytarev density gives you some element like this, and what you do is you choose a basis. Explained very properly. Choose a basis of rho such that rho of tau is diagonal, lambda 1, lambda 2, right? And yeah, lambda 1 is congruent to 1 modulo x theta and some power of t, and lambda 2 is congruent to psi of L, psi of tau modulos. Okay, so once you have this, you get sort of rho of sigma as A sigma, B sigma, C sigma, and D sigma. Plus there's a change of basis matrix. So there exists MP. For every P, there exists a change of basis matrix AP, BP, C sub P, and D sub P, such that this A sigma, B sigma, C sigma, and D sigma times MP is MP times that particular thing, right? So whenever you restrict to this is for all sigma in G sub P. Epsilon cyclotomic to the K minus 1, eta P inverse, psi star 0, eta P applied to sigma. Yeah, so this is the C A over P and C over P are these things. So now Yeah. Most out of time, so let me just tell you what the B module is, and just tell you a little bit about. The place where P equal to 3 is, and there's no simple way around it. So B0 is the TM submodule of K generated by these B sigmas. And then B is just, sorry, that, yeah, maybe I'll denote this by B bar. B bar is the right. I want to denote that by B. Is the module generated by B0 and these APs over CPs. Okay. All right, so so by considering, so you consider, so this, you must have seen this in the proof of main conjecture. So by considering this and this, you prove that A sigma is congruent to this modulo x theta, and then D sigma is congruent to psi sigma modulo the same. And so this is something that, I mean, and this uses, so this uses that lambda 1 is not congruent to lambda 2 modulo the maximal ideal. Oh, yeah, so. So they're certainly not congruent modulo x theta. And this fails when you are at p equal to 2. So you can't prove this congruence. And this congruence is needed to show that yeah, so if you write down what it means for rho to be a representation, you get that B sigma prime is A sigma B sigma prime plus B sigma E sigma, sorry, D sigma prime. And then you write these congruences down, you get that kappa of sigma is, I define it by psi inverse of sigma E sigma. And if you, so this thing is, yeah, again, I'll look at modulo this high power of P. So this is the sigma phi of sigma. So this gives a cocycle with values in B bar psi inverse. You just check it from this. So that's how you get the cocycle. So now you have to prove its local properties, and that comes from this kind of relationship, which I'm not going to talk about. And then the other thing that you have to prove is that what is B bar? Yeah, B. Yes, I have to tell you what B bar is, right? Okay, so so I is the kernel of this map phi from TM to W, and B bar is B modulo IB, and then also somehow the the inertia subgroups at P, yeah, also the inertia subgroups. So, yeah, so actually this is, thank you for asking that because I was wondering what I wanted to. Yeah, the last thing I wanted to say. So this is kind of obvious because you want this congruent, right? So that's why this R comes in here. But you're modding out by more things. You're modding out by all the inertia subgroups. And that's because if you just look at this, you get a cohomology class, but that cohomology class is not unramified at P. That's genuinely ramified. So what do? Well, you just brutally kill the ramification at P, so you get something unramified. But now the problem is you may have killed your module also. You may have made it so small that it's no longer useful. But that's not the case, and that's where this X comes into picture. So that X measures exactly the size of the thing that you kill, and B bar is still large. So yeah, I won't show that calculation, but that's a very nice calculation that you can have a look at.
Yeah,
I'll
so
stop.
this X represents extra congruences than what Wiles gets in its proof of the main conjecture. We get like extra congruences by a factor of X. And then we use that because when we kill ramification, we divide the size of our module by exactly the same X. So kind of, it's important to get the extra congruences to allow you to mod out by the ramification to get something that's still big enough when you mod out.
Then this B bar has a quotient which is cyclic killed by theta, I suppose. Z bracket G minus mod theta.
Yeah.
So that its fitting ideal is inside the ideal generated by theta.
No, I don't know if it's
don't know if it's
cyclic of with.
Cyclic, yeah.
No, I mean we show that the fitting ideal
Fitting
of this
ideal.
is contained in it. And the way we show this is we take yeah, we take a presentation of this and then we show that determinant of each of these minus is killed by phi of u. This and
Yeah.
Yeah, so we actually compute actual determinants defining the fitting ideal rather than a general theory that gives you that it's like the fact that it's cyclic or something. So
No, I didn't expect it to be cyclic. I expected it to have a cyclic quotient killed by theta.
I'm not sure.
but would that
That would imply that its fitting ideal is.
Yeah, but I don't think we can show that.
no, I mean if it's just killed by theta, it won't necessarily be
It has a cyclic quotient killed by theta, which means that its fitting ideal is inside the ideal generated by theta. Because you have a surjection, right?
Yeah, but I don't think we can show that.
no, I mean the structure of this is a complete mystery.
I understand.
Yeah.
I understand.
As usual, like
So you are using this theorem that characterizes elements that are killed by theta.
I mean, I think this is exactly the point that you are making about where Tate came into picture during Maser-Wiles. They were trying to sort of say something about cyclicity of these kind of things, and it still seems hopeless.
Yeah.
So
Yeah, but Wiles has to work. I mean, as you know very well, that Wiles has to work very hard to get the class unramified by like twisting by auxiliary characters, and we kind of avoid that with this other argument.
right, let's thank.
Any other questions for me?